Oil production feasibility. Determining profitability of an oil field. An oil company has agreed on a 20-year contract to lease a field with undeveloped reserves to exploit. Here, we build a profitability case to determine NPV as a profitability measure for this business opportunity. A number of simplifying assumptions have been made, since the emphasis is on explaining a series of at-risk tools and distributions especially designed to handle the typical risks and variables of the industry. Assumptions are provided on geologic reserves estimations, number of wells to drill, declination rates, drilling and operating expenditures, royalties and other expenses and financial assumptions. We first define the profitability model assuming stochastic variability. In other words, we build a NPV model where the key variables have been defined as at-risk distribution functions. Thus, when we later run a Monte Carlo simulation for the model, we will be able to observe upon NPV and other key output variables, the effect produced by all the input variables or moving parts of the model. Analysis and interpretation of the results comes after the simulation is performed and various types of analytical charts are developed. For example, we determine and analyze the production curve along time and the key variables that impact the most the profitability of this business venture. Defining reserves. The Society of Petroleum Engineers gives a precise definition on proved, probable and possible reserves, making these qualifications affected by the geological complexity, stage of development, degree of depletion of the reservoirs, and amount of available data. Proved reserves are those quantities of petroleum which, by analysis of geological and engineering data, can be estimated with reasonable certainty to be commercially recoverable. Under probabilistic methods, there should be at least a 90% probability that the quantities actually recovered will equal or exceed the estimate. In other words, the 10th percentile of the reserves curve represents proved reserves. Probable reserves are those unproved reserves which analysis of geological and engineering data suggests are more likely than not to be recoverable. Under usage of probabilistic methods, there should be at least a 50% probability that the quantities actually recovered will equal or exceed the sum of estimated proved plus probable reserves. In other words, the 50th percentile of the reserves curve, the median, represents probable reserves. Possible reserves are those unproved reserves which analysis of geological and engineering data suggests are less likely to be recoverable than probable reserves. In this context, when probabilistic methods are used, there should be at least a 10% probability that the quantities actually recovered will equal or exceed the sum of estimated proved plus probable plus possible reserves. In other words, the 90th percentile of the reserves curve represents possible reserves. On the other hand, the central limit theorem establishes that if you have a sum of independent and random x variables, this sum tends to possess a normal distribution. By the same token, a product of independent and random x variables possesses a log normal distribution. By definition, a random variable x has a log normal distribution if natural logarithm of x is normally distributed. Just as there are numerous applications of normal distributions, there are a surprising number of situations where log normal distributions naturally occur. As Dr. Murtha points out, in oil and gas modeling, we see this distribution in reservoir volumes, reserves, recoverable hydrocarbons, permeabilities, grain size distributions, and bids on parcels in lease sales. Therefore, under SPE's standard and a log normal distribution assumption on reserves, if information is provided on these three reserve categories, proven, probable and possible, we could build a log normal distribution function for estimating reserves with at-risk distribution functionality.